video just to help out the folks who may or may not know what's going on with the normal distribution and how that's going to be used in statistics. So let's go ahead and start. So what we've covered so far is just discrete. So we've discovered or talked about some discrete distributions. And I'll just rehash those real quick before we start down the normal path. Let's see, X, your random variable. So I'm just going to use X for each one of these. X can be a Bernoulli distribution. The only parameter in that one is P. X can, for another discrete one, X can be a binomial distribution. I'll go ahead and write this one out. Binomial, and the two parameters are N and P. X can be a Poisson distribution. We've talked about that one. Poisson, and alpha T being the mean is the only parameter that goes in there. Or we could have sort of unnamed distribution. And the way that we do that one, right, so unnamed meaning it's not a parametric distribution. The way that we would do that one, here, let me put a little bit of space in here. Move this down. The way that we'd do that one is we'd say, well, X has got some support. So we put the support here, whatever that support is, and then we'd put P of X on this row. So for whatever values we have, whatever those probabilities, making sure that those add up to 1. And then if we're feeling excited about it, we can also put our CDF in there as well. So we've done this we have done these in the past, and so you got X, you got your support probability that capital X is equal to small x. The small x is being here the support, and then you have your cumulative distribution functions on that row. So we've seen those in the past videos. Also, we've talked about some continuous distributions. So all I'm trying to do is get you to where we're sitting at for this particular one. So we've talked about a couple of different distributions. The first one was the uniform. So maybe over here, our X is a uniform. I'll just go ahead and write a couple extra letters. And the first parameter is A, the start of the uniform, and B, the end. So that's a way to define that one. I only need those two parameters. We've also talked about the exponential distribution, where it had just one parameter called lambda, and we've talked about the connection of the exponential distribution to the Poisson distribution in the Poisson process. So we've talked about that as well. And then we know there's unnamed distributions. The way that we want to, or the way that we talk about those, or we give those, is we say, hey, this is distributed, and we either give the PDF or we give the CDF. So either one of those, f of x, capital F of x. So we either give the probability density function, or we give the cumulative distribution function. So one of these two, f of x or capital F of x, we give those two, and we can basically define what that distribution is. Okay, so today's lesson is all about a new continuous distribution, and it's all about, so today we're going to concern ourselves with the normal distribution. And it's a very important one, and that's why it gets its own lesson, its own topic. And then we're going to also, for the next video, talk about how the normal distribution is used in statistics. So statistics, and we will probably develop the t distribution as well in this relationship to the t distribution. So those are the things that are coming up. But today we're super concerned with a random variable x being distributed as a normal distribution with the parameters for the normal. This is pretty nice for us. We don't have to calculate them. Is the mean. So the mean is the one of the parameters, and its standard deviation or its variance. You'll see either one of those two in there. and it's standard deviation as the parameters that go in there, where, just so you remember this, the expected value of x is equal to mu, and the variance of x, let's take the square root of this. So the square root of the variance is equal to sigma, because sigma is equal to sigma squared is equal to the variance of x. So we don't have to calculate these things. They're sort of given to us whenever we could calculate them, but they're given to us if you know what the distribution looks like. Okay, so let's see what the PDF is. So we won't use this a whole lot. We're not gonna integrate this thing or anything else. But it's good to have seen the probability density function. The PDF is equal to let's see, it's 1 over 2 pi, the square root of 2 pi sigma. So sometimes you'll see this sigma squared underneath the square root sign, but I'm just going to leave my square root stop there. And then times e to the negative, and there's an x minus mu quantity squared divided by sigma squared. And I think maybe there's a 2 on there as well. So 2 sigma squared. And the support for this distribution, as you may have guessed, if you sort of look at this function, there's no limits on it. So it's basically from negative infinity x all the way to infinity. So the support for the normal distribution are all real numbers. Okay, let's increase my width here. Let's go down. Let's go down. I need some more room, possibly. I can always come back in here and take it away. So now, the next thing we want to do is maybe draw it. So I'm going to draw sort of a normal distribution. And the top of the distribution, so the top of this line would be where the mean is located. So that's where I tried to put that line. So that would be your mean, and your standard deviation or your variance, depending on whichever one you calculated or you were given, is references how far apart or how much of the distribution lies in this interval. Now, is that the exact sigma? No, you'd have to be able to calculate that, or you'd be given it, or it'd be given to you. And I'll come down. So this will be mu minus sigma, and this will be mu plus sigma. So a certain amount of probability lies between the standard deviation of a normal distribution, and we'll talk about those later. Let me just give you an example of one that has, just because this idea of standard deviation may be new to you, let me give you one that has maybe we'll say sigma is small for this one, for the red one. So most of the distribution lies and this is symmetric distribution, so I'm trying to make it as symmetric as I can on my drawing here, and I don't know if I did a great job of it. So that would be sigma small, and then you might have a sigma that's a little bit larger. Maybe sigma is large. So you would expect it to be, for the distribution to be pushed out. So you expect a lot of your probability to occur in this small window here, whereas if your sigma is large, you would expect the probability to occur in a much larger area. F of x, so your CDF. So we've talked about the PDF, and the way that we get the CDF is capital F of x is equal to, so what would I do here? What is the support? It goes from negative infinity all the way up to some x, And then remember the dummy variables, fy, dy. And again, I'm not going to rewrite this distribution, but that would be the one that you'd put into the FOY, just be y's instead of x's. And the problem with this one is there's no closed form solution. So there's no, like the exponential distribution, closed form solution for this. So what we're going to do is we're going to use R. So we'll find out here in a few minutes. We're going to do some R code. It's not really code. You're just using their way of calculating a normal probability using their stuff. And the variance, oops. So that would be the CDF. And if I wanted to calculate the expected value, which is given, but you could go from negative infinity. It's never bad to throw this out there, f of x dx. So that's how we would get our mu if we didn't know it already, but we do know it. And the variance of x. There's nothing wrong with rewriting these because it's good to remember. So this would be x minus mu quantity squared f of x dx. And the letter sigma squared. All right, so in order to get started here, I'm going to bring this up a little bit, and we're going to go ahead and solve this problem. So it's a company makes electrical resistors that have a mean resistance of 40 ohms and a standard deviation of 2 ohms. The question is, assuming a normal distribution, find the probability that it's less than 37. So the way we model this is we start off with our random variable x, and we define it. So how is this one defined? Well, it would be the resistance of an electrical resistor produced by the company. Produced by the company. And we would note that this is a random variable, so we could be some number anywhere from, well, if we define this as normal, it's going to be anything from negative infinity to infinity. That would be the support for it, but it's going to be very improbable that one that has a mean of 50 with a standard deviation of 2 that it would get net less than 0. So we're going to allow this to be a normal distribution with 40 and sigma. I'm going to go ahead and write sigma here because sometimes you see sigma squared here, but sigma is equal to 2, and these are ohms. You can write them in if you want. And then we're going to find, okay, so we got to write a probability statement now. So our probability statement is, I want to find the probability that x is less than or equal to 37. All right, so what does that look like? I like to draw a simple graph of this bell-shaped curve. I'm not great at it, but I like to do that in order to sort of understand what I'm trying to do. And that's 40, and then I put another number over here representing the number that, so this is our little small x here. So I put that in here. This is your mean. It's the one that's at the top, or the place where your distribution is the highest. And then I like to draw, maybe even in a different color. I like to draw, I can't really tell that one apart. I'll put it in red. I like to say, okay, I'm going to find the probability that I'm inside here. So I'm going to let that be P. So equals to P. So how would I find that? This would also be equal to, if I had the CDF, it would be basically all I had to do is put in my X value here of 37. And we find that we can do this fairly quickly in R. So go to R and find this probability. All right, so let's go ahead and do that. So I can stop sharing, start sharing R. If you come down here and you type in pnorm, So you got D norm, P norm, Q norm, and R norm. D norm is the density function, and you don't necessarily need that one for anything unless you're gonna then integrate it. So in general, we're gonna use P norm, we're gonna use Q norm, and we're gonna use R norm for different things. Today's lesson, we'll use P norm and Q norm. So in this case, we're gonna find P norm, and then look and see what it has up there. So Q. So they're just calling the value that's in your x-axis Q. No one knows. Well, I don't know why. And then if you don't put anything else, it assumes your mean is 0 and your standard deviation is 1. We're going to tell it what our mean and standard deviation are. So in our case, so 37 is going to be the number that we're putting in from the number line, and 40 is our mean, and 2. Oops. So 40 is our mean, and 2 is our standard deviation. And so we get 0.067. So that's our probability that we're less than 37. So 0.0668. So let's go back, start sharing our OneNote, and we find out that this answer, this probability that sits in there, is just 0.0668. All right, so that's our answer to that one. The probability that we're less than 37. So again, interpret. So you take this and say, well, 6.7% of the time, a randomly selected transistor would be less than 37 ohms. Do the same thing here. So we're just going to use the random variable above, the random variable definition above, and the fact that we know it's the same distribution, and we're going to write a new probability statement here. So the probability that x is greater than or equal to 43. Now, because I know the normal distribution, I don't know if I've said this or not, but the normal distribution is symmetric, meaning the amount of probability on the left is equal to the amount. So the amount of probability on the left is equal to the amount of probability on the right. There's 50. So the mean is also equal to the median. The 50th percentile is the median, and is also the mean, right? So there's 50% of the probability lies up in here. And this number, it's on this side, that probability is going to be equal to the amount of probability. So it's symmetric, meaning that it's, if you took the mean and drew a line, the part on the right would look like exactly the part on the left. And because I know that this is going to be equal to 0.0688. And so let's look and see how we would calculate that, though, because that's the point of this particular exercise. Is one, I wanted to talk about symmetry, and I also wanted to show you how to find one that is on the other side. So I got my little bell curve here. I'm going to put my 40. I'm going to put my 43 here. Now, again, pictures aren't exactly, but what I'm looking for is red. So I'm looking for this probability. So I know that if I took, here, we'll put it in a different color, this probability up to 43, this is equal to F43. And I know that F43 plus P is equal to 1. We know this. Why is that? Because all the probability that I put on this distribution, the probability from negative infinity to infinity has to add up to 1. And that's why I know that this guy has to be 1. So if I'm looking for P, the red one, then I'm just going to simply solve for, so P is equal to 1 minus F of 43. So the idea here is if you're in the right tail, like this problem is, if you're in the tail to the right, then you need to do a 1 minus the left tail basically, and it's not really a tail here, but the probability to the left, and where this represents the probability to the left. Okay, so let's do this. 1 minus, I think it's p norm. So just go to your computer, 43, 40, comma 2, and see what we get. All right, I'll do it as well. One minus p norm, comma 2. And we see that we get exactly what we thought we were going to get. Not that calculating these things are very difficult, so I just wanted to show you that the symmetry part is a thing. And why is it symmetric? Because there's 3, the distance of here is 3, and the distance here was 3, and that's how I knew that those probabilities were going to be the same. Okay, so the next piece is trying to figure out what the percentile is. And the thing about the percentile is it is a different way of looking at the same problem. So let's find the 25th percentile. Same x, x is still defined the same way. Same. X is still distributed as a normal 40, comma 2. So I don't have to do any. You don't have to do this again well, you don't have to do this part again if it doesn't change from the previous piece. But what we want to do now is we want to find the probability that x is less than or equal to some number, and we're going to call this 0.25. So I don't know what this guy is, and I'm trying to find the 25th percentile. So I'm just going to name this x of sub 0.25, and we know we want that to equal, we want this probability to equal 0.25. So let's draw on a graph here what that looks like. Another bell curve. You would think I would get better at drawing these, but I do not. So 40, and we're looking for some number, and because it's less than 0.5, I know it's going to be to the left over here. Let me grab a different color. So I want this probability in here to be 0.25. So 0.25 probability, and what we're looking for is the x value 0.25 that goes along with that. So it's sort of the opposite of what we've done previously. We were given the x value like 43, and we're trying to find the probability that lies in one of the two sides of that 43. Well, in this case, we're given a probability. We're given a probability this time, and we're trying to find the x value that goes along with that probability. So it's sort of like the inverse problem. So what does that look like in R? I mean, a way of doing it would be to, if we owned the CDF that we could integrate, then we would basically integrate and find, or we'd use the CDF, right? So there's another way to say it's like, hey, I'm looking for x of 0.25 that equals 0.25, and we'd solve for that. So if we knew what the CDF was, we would just solve for the x. We would put the CDF on this side and the 0.25 over here, and we would solve for the x value that gave us that number. In this case, again, we don't have the closed form solution for the normal distribution, so we're just going to use, again, we're going to use R. So R built in this Q norm function for us that does that. And so what you do is you put the probability that you're interested in here, and then you put the parameters for the distribution in, and this would spit out the value, the x value that goes in right there. And it's always looking to, this is the probability to the left. Probability to the left. In other words, if you're looking to the right, if you're looking for this probability, then you'd have to do a 1 minus if you're trying to go the other way. And we'll see an example of one of those here right after this one. So we'll come back and we'll do this one in R. So let me go ahead and write that down. Q norm 0.25 40 comma 2. Okay. Before we do that though, let's look at the next one. So I'm trying to find two of them. I'm trying to find the 75th percentile. Using the same business, right? So let's see what that looks like. So again, this is 40, and because our probability, so probability of x is less than or equal to some number, we don't know what it is, but we're looking for it, is equal to 0.75. Because this number is bigger than 0.5, we know it's to the right. So this will be our x 0.75, and this probability over here, we want this to be 0.75 probability. So f of x 0.75 would equal 0.75, and then we would take our CDF and then solve, right? And so in this case, it's also going to be Q norm 0.75 comma 40 comma 2. And I claim that I can sort of already know what the answer to this one. If I know this answer, because of symmetry, then I can probably figure out this one. Why? Because if 75% lies over here, that means there's 0.25 probability over here. And the same thing over here, if 0.25 is on this side, that means 0.75 is over here. So let's just see, and then what does that mean? That means the distance from 40 for both of these are going to be the same. Okay, and so what we'll do is we'll find out 0.25. I'll make my prediction on what 0.75 is going to be, and then we'll see if it comes out to be the same in R. Okay, so move back over to R. Again, this is Q norm 0.25 comma 40 comma 2, and it's 38.75. So 3840 is here, 38.75 or 65, that gamut, 65. So give me 40 minus that is 40 plus control V. So my prediction is that it's going to be 41.34898. All right, let's see what happens. So Q norm 0.75. Let me move this out of the way. Oh, 40 comma 2. All right, look at that. So it gave us what we thought we should get. So let's go back to OneNote. All right. So the next thing we want to talk about is another. It's not really another distribution because, I mean, basically it's the same distribution as this one. It's just sort of refining it or talking about it in a different format, if you will. So I'm going to draw a big giant line here, right here, and then we're going to talk about the standard normal. Standard normal. And as you can imagine, a standard normal has a standard number for its mean. So we have a mean of 0 and a standard deviation and variance of 1, right? Because the square root of 1 is 1. So the mean and generally people say the standard deviation of 1, but they also mean sigma squared. So so it looks like this. It's a normal 0, 1 is a standard normal. The way you get a standard normal is if x, well, there's lots of ways to get a standard normal, but the way we're going to talk about it is if I give you a normal distribution with mean of mu and a standard deviation of sigma, then I'm going to do a transformation. So I'm going to do a transformation by taking x, taking my random variable x, subtracting the mean, and dividing by the standard deviation. And if I do that, the new variable, the new random variable that comes out of here is going to be a z distribution. And so there's some math to be shown that this thing is that this new random variable is normally distributed, right? So there's math that we're gonna cover. We could, but it's just not it's not useful for us. So math involved to show normally distributed, and it's not hard math. It's just more than I'm willing to do right now. Distributed. But we will do this. We will show why that the expected value. So I will show you this. I will show you the expected value of z is equal to 0 based on this and the variance. Not the variance, but the standard. Yeah, the variance. We'll also show you the variance of z is equal to 1. So I'm going to show you that. So let's start off with the expected value. So I got the expected value of z is equal to the expected value, and all I'm going to do is take this guy and throw him in here. So I get x minus mu over sigma. And if you remember from our class when we started talking about expected value and the linear operator, you remember when I take if I don't have any, if it's a constant, then I can just take it out of the expected value. So I'm going to take 1 out of sigma out, and the expected value of x minus mu is equal to 1 over sigma, the expected value of x minus the expected value of a constant. So mu is a constant. There's no random variable in there, which is equal to, this is quantity. And we get 1 over sigma quantity, expected value of x. We know that that one is expected value is mu, right from right here. And then minus mu, because the expected value of a constant is just a constant. And then we get this guy goes to 0. So the expected value of our z is 0. So expected value of z is 0. Okay, the next thing we want to do is the variance. So we're going to use the same rules that we had the other day on the variance. So when I take the variance of x minus mu over sigma, I know that when I take a constant out of the variance that I square it. And if you don't remember that, go back to the video and check it out. And then the variance of x minus mu, and you can kind of see where we're going with this. So 1 over sigma squared, variance of x minus the variance of a constant. So what is the variance of a constant? It goes to 0, and it's sigma squared over sigma squared, which is 1. So I haven't shown you the math that's involved to show you that it's normally distributed, but I have shown you why the expected value of this transformation here turns into the expected value turns into 0, and the variance turns into 1, which are the most important things involved in this sucker. Okay, so let's go back to our example and use A. So we'll use this transformation in order to find a probability. I believe A was the probability that X, and this is to give you practice on, at least to see how to do subtractions and whatnot inside a probability statement, because it's not any different than what you would imagine, like how you would do a probability, or if you're going to do algebra, you can do algebra inside the probability statement. So in this case, I'm going to let probability, so we're just going to transform this variable. So I'm going to subtract mu, I'm going to divide by sigma, and that's less than or equal to, so what is mu in this case? I believe, if I remember correctly, it was 40 divided by 2, and so that's equal. So again, we take this, and we know that sucker is this capital Z now, and this is whatever it is. And so I believe that's 3 divided by 2. So we turn that in, this probability statement turns into what's the probability, the random variable Z, which, oh, by the way, we know Z is a normal 0, 1, that it's less than or equal to 3/2. So that's the question. The good thing about R is, or I don't know if you remember, but when we looked at it, it said something to the effect of, let's go ahead and say 0, the mean is 0 and the standard deviation is 1. So if you don't put anything else in there, if you just do p norm 3/2, you should get the same probability that we got above. So let's remember what we got. I don't remember, 0.0668. So that should be 0.0668. And we'll see it here in a second. So all I'm going to do is, I'm not going to worry about the parameters that go in here. I'm just going to put in p norm 3/2, and we will get the standard normal. And that's why it is called the standard normal. Well, I shouldn't say that's why it's called the standard normal. It's the standard thing that's in the R. If you don't put anything else in there, it's going to give you the number for standard normal. All right, and let's see what B is. So B is the random variable X is greater than or equal to, again, we're doing this for practice, is equal to the probability. So all I'm going to do is take my random variable X, so I'm subtracting mu divided by sigma, which is greater than or equal to 43 minus mu, in this case is 40, divided by sigma, is equal to probability that Z is greater than or equal to, guess what? Oh, I forgot, this is a minus. That should have been a minus. Because it's on the left-hand side, and 37 minus 40 is a -3. This one would be +3 divided by 2. And that is going to be equal to 1 minus the probability that Z is less than or equal to 3/2. This one is a +3/2, so it's going to be on the right-hand side of the mean 0, and the -3/2 is going to be on the left-hand side. But the amount of probability in each one of the tails is going to be exactly the same. So that's how I'm getting the tail, because I'm doing 1 minus, and it's going to be 0.0668. Let's prove that to ourselves. Yeah, let's do that one first. Those two are basically the same problem. So let me write it down. So I'm doing p norm of -3/2, and then 1 minus p norm of 3/2. Yeah, I forgot to write that in. So p norm in R of 3/2. So let's stop sharing, start sharing R. What do we get? P norm -3/2 minus P norm of 3/2. And we see that we get exactly the same thing, what we thought we were going to get. All right. And then finally, part C. Let me draw a picture. So I apologize. I just should have drew a picture. You're supposed to draw a picture when you do these probabilities. So this one's 0, and this one is -3/2. And the amount of probability in there is 0.0668. And then this one is the other side. Not drawing the scale, I apologize. And this one's 3/2. This one's 0. And the probability in here is 0.0668. Which makes sense, right? If it's a symmetric distribution, then the amount of probability on this side is equal to the amount of probability on that side. All right, so let's look at the next one. I think we were doing the quantiles, or correct? Let's just do one of them. We'll do the probability that X is less than or equal to X 0.75 we'll say that was, we wanted that to be equal to 0.75. And how can we do that? Well, again, we're going to do the same thing. We're going to transform this variable into a standard normal. Subtract mu divided by sigma is less than or equal to x 0.75 minus 40 divided by 2 is equal to 0.75. And this would be the standard normal of x 0.75 minus 40 over 2. So this would be p norm of whatever's in here. But the problem is we don't have 0.75. We don't have numbers to go in there right now. So what we want to do is we want to do the inverse. So I talked about that earlier. We're going to do the inverse. So so the inverse of the standard normal and the inverse of the standard normal 0.75. This is called Q norm. And these two go away and just leave you with x 0.75, because when you take the inverse of a function, it just leaves you with whatever goes into that function. So we're just left with 0.75. 40 divided by 2 is equal to inverse function, which is our Q norm, 0.75. So let's go ahead, so Q norm, and I don't have to put the parameters are in there. I can just put 0.75 in, and we can find out what that sucker is, and we'll come back and solve for it. Okay, so let's do that one. Go about, go into R. So Q norm 0.75. We'll enter. So I'm getting 6.744. So 0.6744898. All right, come back out, go into OneNote, and so our answer to this sucker, so this was 0. Where did I put it? 6744898. Okay, I've written a whole bunch of numbers there. But what I'm trying to solve for is x of 0.75. So what that is I'm going to take this, which is that 0.6, that long sucker there, 6744898, and I'm going to multiply that by 2, and then I'm going to add 40 to solve for that. So I claim that should be the same thing that we got above. What was the number that we got above? Did we ever do that one? Maybe we did it and I just didn't write it down. That's probably what happened. So we'll compare notes here in a second. So I'm going to solve for this guy, and I get 40 plus 2 times 0.6744,878. 41.3. So 41.349. Okay, let's go back to R. I know I'm jumping back and forth a lot. Let's see what this one. 41.34898. 41.34898. 41.34898. 41.34898. 41. Oh, there it is. 41.348. Yeah. So we got the same answer. Okay. So that gets us to doing the standard normal. Now the last thing that I need to do is prepare you for statistics, because that's what we're going to talk about next time. So now we need to show how this normal distribution is used in the world of statistics. Actually, we won't do that yet, but I'm going to prepare you for being able to do that. So what I'm going to do is I'm going to define this thing called So define this thing called Z alpha, because when we start doing these confidence intervals, we're going to need to know what this is. And the only thing this is it's the Z value. So think of this quantile business here. So like this guy was 0.67488878. That was the number that was, so that was the number that was on the line, but it wasn't the Z alpha number. Okay, so what it is, let me draw a picture. All right, if this is my Z alpha number, then all we're doing is we're saying, okay, that is the number on the Z axis. So again, this will be 0, and this will be that has alpha probability in the tail. So that's all we're looking for. And we're always using the positive one, and that's why we're coming to the right-hand side. I mean, we could easily find the negative one, but I mean, when we start doing these confidence intervals, you don't want to be messing around with the negative Z alpha, which would be the amount of alpha that's in that tail. So just understand that we're looking for the positive number, and that's why we're looking for the amount of probability that's in the tail. So let's do an example. So we'll let Z alpha here. I got an alpha for us, so we'll just think of one off the top of our head. Oops. We'll do Z, and I'll do a weird one. I don't know, 0.0055. We'll try to find that guy. And what does that look like? Again, I love drawing these bell curves. You'd think that, like I said earlier, that I would get, oh, that's a horrible, I can't live with that. I get better at this, but apparently I don't. Sometimes I come out with a good one. Oh, I almost came out with a good one that time. So what I want is 0.0055 probability in this tail, and I'm looking for this guy. So how would I find it? Well, it's the inverse function, right, of what? Well, I can't put 0.55 because this would, what that would be is this number way over here, right? I would have 0.5. I need to do 1 minus this guy because that's the amount of probability. So that's the percentile, if you will, of this number. So it needs to be 1 minus 0.0055. I didn't mean to make that blue. Which is equal to the inverse of 0.9945. Yes, I do need a calculator sometimes to do this. And then so Q norm of 1 minus alpha, basically. So Q norm of 1 minus alpha gives us our value. So we'll jump over to R real quick. 0.9945, 0.9945, 0.9945. So Q norm 0.9945. And we get the number 2.542699. Okay, if we go to the back of the book, so most statistics books have a table in them. And if you were to go back in the back of the book and look up, so you go into the table and look up 0.9945, you would find that that 2.54 would be the number, and it would stop there. But ours goes a little bit deeper. So this number here, 2.54299, is the number that gives us that amount of probability in the tail. Okay, I hope you enjoyed the video. That's all I got for the normal distribution, at least today. Next class, or next time that we talk, I'm going to be going through how we're going to use this normal distribution to find confidence intervals, and then we'll connect that with the t-distribution and basically most of the time use t, but you have to understand the norm and the normal distribution before you can really understand the t and how it's being used. All right, hope everybody has a great day.